We've seen that the Biot-Savart law is to magnetic fields, as Coulomb's law is to electric fields. So one might reasonably wonder if there's something that plays the same role for magnetic fields as Gauss's law does for electric fields. And the answer is yes, sort of. Gauss's law is a statement about how the electric flux through a closed surface is related to the amount of charge enclosed by that surface. But there isn't really a thing that corresponds to charge for magnetism. You never have, for example, a north pole sitting there by itself, shooting field lines radially outward in such a way as to get a positive net flux through some enclosing shape. Instead, you have things like bar magnets that have norths and souths, such that if you enclose the magnet with a shape, you get as many field lines going in as you have going out, which leads to zero net flux. If you're clever, you might try to isolate one of the poles by breaking the magnet in half. But that just makes two more sets of norths and souths. And if you keep smashing things all the way down to the level of an individual electron, you find that even a single electron has an intrinsic north and south pole, which is just super. So at the end of the day, we're forced to conclude that since there doesn't appear to be such a thing as an isolated north or south, which is what we'd call a magnetic monopole, it must be the case that the magnetic flux through any closed shape is always zero. So that's the kind of sort of correspondent to Gauss's law. It actually is one of the four Maxwell equations, and it's considered quite important on account of how it expresses the fact that magnetic charge equivalents don't exist. There's no magnetic monopoles. But since it always gives us zero, we don't use it that often in an intro class. There is, however, another law that doesn't look exactly like Gauss's law, but does let us solve for the same kinds of things as Gauss's law does. We call that law Ampere's law, and we'll return to it another day.